Welcome. Today we're going to talk about the first derivative and what it means for the function. And then we'll use it to design what's called the first derivative test. It's used to find local mins and maxes. So, what do I mean by looking at the first derivative? Well, we've kind of talked about this a little before, but basically there are some properties here. When the derivative is positive, the function's increasing. And when the derivative is negative, the function's decreasing. Those are the two that are important. When the derivative is constant, when the derivative is zero, for a whole interval, rather than just being zero and going on, it can be constant there. This is not a common thing to happen, so we don't really worry about that rule. Basically, this is the analysis I want. If you've got a function, then look at the derivative. It's positive here. It's positive, so the function's going up. This is not this causes that. That also causes that. They're back and forth. And then the derivative turns zero briefly, and then it goes negative. So it's going down. It's decreasing. Then it turns zero. Then it goes positive. So now it's increasing again. We can use that positivity and the negativity of the derivative to talk about when the function's going up and when it's going down, and therefore find the max and min points. Notice they're at where the derivative is zero, but the derivative being zero is not enough to tell us exactly which one's what. And you could graph it and you get an idea, but sometimes the graph doesn't work. Sometimes the graph is not enough to tell you for sure because it's too complicated, too messy, or you can't get into it. Another important property that's necessary for the derivative here, if you recall, there's something called the intermediate value theorem. Intermediate value theorem said if you have a continuous function and you're positive here and you're negative there, you had to pass through zero. It said more than that, but that's essentially it. If you're positive here, you're negative here, you pass through zero. So another way of looking at that is if you know where every zero is and it's positive there, it's going to be positive in that whole way. We'll talk more about that in a second. Derivatives are not necessarily continuous. You don't have to worry. All the derivatives we ever talk about will be continuous. But they have, even if they're not continuous, the intermediate value property. So basically, they use the intermediate value theorem. They ignore the condition on it has to be continuous. And they say, but we're still getting to the conclusion that to go from positive to negative, you have to pass through zero. Why is that useful? Well, it means that we can look at the derivative and only find the zero spots, and then we're confident about what the shape of the graph is. All of this leads us to what's called the first derivative test, which allows us to find and decide what the local mins and local maxes of our graph are. So first, the way we do this is we find the critical points. So we take the derivative, find it, and then we set where it's equal to zero or doesn't exist. These are all the critical points. So we find where the derivative equals zero or where the derivative doesn't exist. Stands to reason that if we found all the spots at zero or doesn't exist, everywhere else it exists and it's not zero. So it either exists and is positive or it exists and it's negative. That's everywhere else. Then what we're going to do is we're going to put these on a number line. And we're going to take marks at these spots, whatever they are. Those are the only spots where it can be zero. Everywhere else it's plus or it's minus. And it has the intermediate value property, so if it's plus right here, it can't suddenly turn to negative. It has to pass through a zero or it does not exist to get there. So if it's plus at this point right here, it's going to be plus throughout that whole region. So we can make a number line with regions in there and test a single spot in each one and know that the derivative will be positive in that whole region or negative in that whole region with only testing once. That will help us determine whether the function's increasing or decreasing there, and therefore for each critical point to decide what's going on and whether it's a min or a max or not. That's what all the rules are. Let's talk about the example and work through it, because I think the example will clear up what I'm trying to say better than talking about the example. So I want to find where this function has any local mins or local maxes. The first thing I need to do is take the derivative. So I do that, I get 10x to the fourth plus 20x to the third minus 30x squared. Did I do that right? 10x to the fourth, 20x cubed minus 30x squared, and the 3 doesn't matter, it's on there just for show. It doesn't have anything to do with the derivative. This is a polynomial, it's going to exist everywhere, so what I really want to know is, where is that 0? hopefully you can see, I can factor some things out immediately. I can factor a 10 out, but more than that, I can factor x squared out. Now, this one was chosen nicely. Most of them aren't as pretty. But the truth is, I need to know where this is 0. I can further factor this part, I hope. Let's see. If I want to factor it, x and x, minus 3 means I've got a 3 and a minus 1, or a minus 1 and a 3, or, well, I want a positive 2 here, so I want probably a positive 3 and a minus 1. Does that work? Yeah. So that means x is 0, or from here, x is going to be minus 3, or from here, x is going to be 1. What does that tell us? Those are the critical points. Now remember, the critical points, these are actually x values, not points, but we call them critical points anyway. The next step is to put them on a number line. And you want to make sure you put them in the right order, because numbers are in order. Minus 3, then 0, then 1. Notice I haven't put them to scale. The scale doesn't matter. What's important here is it divided the number line into 1, 2, 3, 4 regions. Each region is either positive or negative. It can't be, doesn't exist because we found those. Well, there weren't any. It can't be 0 because we found all of those. And it can't switch from plus to minus in here without passing through 0, and it only passed through 0, there, there, and there. So each region is always positive or always negative. We're doing this on the derivative, so I'll write f prime here to remind me that I'm looking at the derivative each time. I just need 1 point from each region. So over here I could try 2, here I could try, I don't know, half, here minus 1, and here, I don't know, minus 35. It doesn't matter what point I pick. Minus 35 is kind of silly, but it doesn't matter. And I just want to know if the derivative is positive or negative. I don't actually care the value, just the positive or negativeness. So let's take this minus 35. I'm going to use this as the derivative. Why? It's factored. It'll be easy to tell positive and negative from this. Put a minus 35 in here, 10, that's always positive. Minus 35, it's squared. Actually, the x squared, that's going to be always positive. So let's put minus 35 in here. Minus 35 plus 3 is negative something. Minus 35 minus 1 is minus something. Positive minus minus multiplied together gives me plus, positive. So I'm going to put a plus with a circle around it because that's easy to work with. The next one, minus 1. Positive, positive. That's positive. And that's negative. Positive times positive times positive times negative will give me a negative. Next one's a half. That's a little harder to work with, but we can do it. Positive, positive, negative. Multiply together, we still get a negative. And then 2. Positive, positive, positive. Everything's positive. And there's the pluses and minuses of the derivative. That's not actually the goal. The goal is to tell about mins and maxes. So now I'm going to draw arrows based on this. We know when the derivative is positive, the function's increasing. We don't know exactly the shape, but we know it's increasing. So I draw an arrow to represent it's going up. Minus means it's decreasing. And again, I don't know if it's going fast, slow. It doesn't matter. I know it's going down. And likewise here, it's going down and then going up. Now you could have put these down here, but again, I don't want to give the impression that this is literally the graph. This is the directions of the graph, but it should tell you what's happening right here. Goes up, then comes down. This is a local max at x equals minus 3. How about over here? That's a local min. How about here? At 0, it's coming down, flattens, and then it goes down again. This is not a max, it's not a min. You'd have to go up, down to get a max, down, up to get a min. This one's a down, and then a down. It's just a flat point. Hopefully this one example gives you an idea what to do, and you can try it out. Till next time, this is Dr. Joe.